Now we are going to talk about regularization. Okay, so far we discussed gradient descent. So we touched regularization a little bit here and there in every lecture. So let's talk about regularization in detail. Okay, now as we already know, so why do we do regularization? Okay, maybe this is a quick review question. So why should we do regularization? Any answers? Yeah.
But the coefficients are too big.
Okay, in the linear regression case, but what is the more general reason? Yeah, to avoid overfitting, right? So we do regularization to avoid, but we cannot totally avoid. So let's just say to control overfitting as much as possible. Okay, now the general way in which people add regularization is like your total error function is going to be something like this: ED of W, which is your error from the data set, okay, plus lambda times EW of W, okay, where this lambda is the regularization coefficient. And this function is a function of your W, the parameters, okay? You can have any function which controls the parameter, and you have this lambda term which decides how much importance you are giving to this function, okay? Now, let us just consider the least square or sum of squared error function as an example for the data function. So ED of W is given by Y minus XW transpose Y minus XW, okay? So I should put a 1/2, like I'm not doing this here. So maybe like this is like one time to reiterate my notations because there were questions about notations in the break. The question was sometimes I use W transpose X, sometimes I do XW, sometimes I do WX. And if you see books and papers, they all have different notations. Okay, there is no agreed notations for these things. Like whenever you have doubt about the equation, just try to write the axis, row axis and column axis. Is it an n cross p matrix or a p cross n matrix? And then you will see that there is only one right combination. So that is what it is. Okay, so similarly, like you will see me using 1/2 whenever I want it, and I will skip it whenever I don't want it. Okay, so that is just for inconvenience. So just for convenience, I can put 1/2 here, but for this discussion, we don't need that, so I'm skipping it. But it doesn't mean that this is a new loss function. It's the same loss function. Instead of putting this 1/2, like I'm just not using it here. Okay, like as you can see, if I have to differentiate, then I will start putting 1/2 so that my differentiation like has this two thing cancel. Okay, so now I think we already introduced L2 regularization, right? Like even in the previous lecture or the lecture before that, right? Like I don't remember. So L2 regularization is basically W transpose W, okay? Which is W square, right? Like for each parameter, you do W square, and you try to minimize this as much as possible, okay? Now, this means that my optimization problem is minimize the loss function, which is Y minus XW transpose Y minus XW plus lambda times W transpose W with respect to W, right? So let us just call this a star. We have already seen this star in the previous lecture, but then I told you there is a closed form solution. We will derive it later, right? So we are going to derive that closed form solution today. So it's very simple. So we are just going to differentiate this with respect to W and set it to 0. Okay. Now, when I differentiate the first term, it becomes, if this is Y minus X the whole, like Y minus XW the whole square, right? So it's 2 times Y minus XW. Okay. When you differentiate Y minus XW with respect to W, you get X. So I put X transpose here, and there's a minus sign as well. Okay. Plus, this is W transpose W, W squared. So it's 2 times W. So 2 times lambda times W is equal to 0. Okay. Now, since this term is equated to 0, I can just ignore the 2's, right? And this becomes X transpose X, okay, plus lambda I times W is equal to X transpose Y. Okay, well, maybe instead of skipping this step, let me write the step. So in this case, this becomes minus X transpose Y, okay, minus times minus, like plus X transpose XW plus lambda W is equal to 0, right? So X transpose X W plus lambda W is equal to X transpose Y, right? So now I can write X transpose, oh yeah, so okay, X transpose X plus lambda times I W is equal to X transpose Y, right? So now I can find W. W is basically X transpose X plus lambda I inverse X transpose Y. So I is the identity matrix, okay? Now, this is my solution for least squares with L2 regularization. Now, can someone tell me what was the solution for least squares, just least squares, without L2 regularization? Without L2. Yeah? Yeah, so it was basically X transpose X inverse X transpose Y, right? So as you can see, all that L2 regularization is doing is to add a positive constant to the diagonal of X transpose X before inversion. Okay. Now, if you have done a basic linear algebra course, you know that this makes the problem non-singular even if X transpose X is not a full rank matrix. Okay. So if you add some positive value to the diagonal, okay, then this makes the problem non-singular even if X transpose X is not of full rank. Okay, so this type of L2 regularization has many names in the literature. Okay, so some textbooks will call this as L2 regularization. Some people will call it as ridge loss, okay, or ridge regression loss. So some people might call this as just weight decay. Whenever people say we are doing weight decay, it just means they are using L2 regularization. Okay, now we had this objective function, right? So this is an unconstrained optimization problem. Okay, now there is an equivalent constrained optimization problem. Okay, one can think of. So let me quickly write that. So now the constraint. Well, maybe first let me write the unconstrained problem. So there are two ways to look at this L2 regularization. So one is unconstrained optimization, where you basically have minimum of W, Y minus XW transpose Y minus XW, plus lambda times W transpose W, right? Now, there is an equivalent constraint optimization formulation where you will minimize the loss Y minus XW transpose Y minus XW, okay, subject to some constraints. Okay, the constraint is W transpose W should be less than or equal to some eta. Okay, now can someone tell me what, like in 2D, so what is this equation? W transpose W is less than or equal to some constant. So in 2D, when I say W transpose W, let's say W square is equal to 2. Or in 2D, there are two parameters, right? Let's say W1 square plus W2 square is equal to 2. What is this equation? Sorry? No. X squared plus y squared is equal to r squared. So what is this equation? It's an equation of a circle, right? Like so in 2D, this is a circle. Okay. So now the radius of the circle is going to be defined by this eta parameter. Like so, you want something which is less than eta. So or in other words, like depending on how you move the eta, okay. So you are going to have this hard constraint. Like so, for example, let's say depending on my eta, let's say this is the circle. Okay. Now this circle is my constraint. Okay. Or in other words, whatever eta I fix, let's say I fix phi, then that gives me a space in the parameter. Now I can only find solutions which lie within this space. Okay. Now, depending on how strong is my regularization, this circle is going to become smaller and smaller. If the circle is really small, I cannot have very high values. If the circle is large, then I can have very high values, right? Now, the original solution, the unconstrained problem solution, right? Like, so it could be somewhere here. Okay. So this is my W if there was no regularization. Now, the regularization tells me that this W is not allowed, right? Then how would you find the W that is closest to this W and is still allowed? So it's going to be somewhere here, right? Like you try to, so you want to, like, so basically you want to stay within this region of parameters, but you want to achieve this solution. Okay, well, it is not possible because you have a constraint here. So you will try to move as close as possible to the solution. And this L2 regularization tells you that, okay, you cannot move after this. Or in other words, this is going to be equivalent to saying, oh, your weights cannot be this large. It has to be only this large. Okay, so then you find this to be your solution. Okay, now this solution is basically the point where the contour from your loss function, right, intersects with this particular constraint. Okay. Now, one can easily show that this eta is proportional to 1 over lambda. Okay. So the lambda that you see here, right? So you increase the value of lambda, then the constraint is larger, which means the circle is going to be smaller. So n is inversely proportional to 1 over lambda. Okay. So as you increase the value of lambda, the circle radius is going to decrease. So you're going to have smaller and smaller weights. Okay. So is it clear? Any questions about this geometric interpretation of L2 regularization? Okay. So now you're going to implement this L2 regularization in your assignment. Like it's really simple. You take the existing code for regression, add lambda I. That's it. Okay. Now, this is not the only possible regularization. Okay. So there are many other ways to regularize. Like another common regularizer that people use is L1 regularization. Okay. So in the case of L1 regularization, my error, the regularization loss is going to be simply absolute value of W. It's like L1 norm instead of L2 norm, okay? So my loss function is going to be minimum of y minus xw transpose y minus xw plus lambda times absolute value, okay? Now, unfortunately, there is no closed form solution for this because of the non-differentiability of this error function, like at w is equal to 0. There is no closed form solution, okay? However, you can compute like gradients in other places other than w is equal to 0. So you can use L1 loss. Like if you are using any standard packages, it would have L1 loss. Like it is just that it doesn't have a gradient at w is equal to 0. Okay. Now, what would be the corresponding unconstrained version of this function? Okay. So the unconstrained optimization is going to be minimize w, y minus xw transpose y minus xw, subject to the constraint instead of W transpose W less than or equal to eta is going to be absolute value of W less than or equal to eta, where again eta is going to be inversely proportional to 1 over lambda. Okay, so now can someone tell me what geometrically what does this equation mean? Let's take 2D. Okay, so in 2D it says absolute value of W1 plus W2, like absolute for W1 plus absolute for W2 should be less than or equal to some value. So what kind of figure is this? Okay, there is some answer in the chat. Is it a square? It's not a square. Yeah.
A square, but like this.
Sorry?
A square, but you twist it by some degree.
Yeah, it's a kind of tilted square. Okay, but there is a standard term for these kind of figures. It's a simplex. Okay. Now, how would that simplex look like? I think he already rightly described. So in this case, like the simplex will look something like this. Like you take any possible x and y, the sum should be capped. Okay, which means it is going to be something like this. Okay. Now, again, let's say this is my W hat. Now, this simplex tells us that you can only find a parameter configuration within this bounded box, but this is the solution that I want to achieve. Okay. Now, as we have seen before, the solution that will be found from L1 loss is going to be some place where the loss function interacts, right? Like so. Now, with this loss function, it looks something like this, and it's going to approximately touch in one of the like edges. Okay, so now this is in 2D, but in high dimensional scenarios, like often the solution will be found in axis. Okay, so in other words, in axis your weights are 0 for these parameters, right? Like so, L1 regularization will give you sparse models. It is going to set, depending on how strong is your L1, it is going to set many features to 0. Okay, so if you have very strong lambda, then a lot of features are going to go to 0. Or in other words, L1 regularization is automatically doing new feature selection. So it is going to find which features are less important, and it is going to suppress them by giving 0 weights. Okay, so one way to do feature selection to remove irrelevant features is by just using L1 loss. If you use L1 loss and like just increase the value of lambda, it is going to set a lot of parameters to 0. Okay, is that clear? Okay, so any questions about regularization?
Sir,
Yep.
maybe you may remind us why we have the two terms in the EO function, the total EO function.
Sir, can you please repeat?
Meaning, the real meanings of having E2 and W.
Sorry, can you repeat?
We have at the beginning the total EO function in terms. Can you remind us the meanings of
so why do we have two terms in the error function? So the first term is your actual loss that you care about, right? So, and this is your regularization loss. So if you don't have the regularization loss, you're going to overfit. Okay, so, well, I think that concludes our discussion on regression, gradient descent, regularization, and so on. I know a lot of you hate that I start topics in between, but well, this is probably the 4th time I'm teaching this course, but still I haven't learned how to stop for break when I finish the topic. So I'll eventually figure it out. So, but we are going to start with like new topic now. So far, I showed you some example algorithms for classification and regression, right? Like, so in the case of classification, can someone remind me what algorithm we discussed for classification? Yeah.
Logistic regression and k-nearest neighbor.
We have not discussed logistic regression so far.
Sorry.
Okay. So we have seen k nearest neighbors, right? Like for classification. And for regression, we have seen linear, like least squares, like which could be linear, nonlinear, depending on the basis function, right? Like so. Now, I don't want this course to be a laundry list of algorithms, okay? So there has to be some unifying underlying principles behind how these algorithms work and how to design these algorithms, right? Like so, that is what we are going to see today. So I should probably warn you that this is one of the two most theoretical lectures of this course, but I will try to make it as visualization oriented as possible by giving a lot of pictures. But we are going to do some theory, okay? So we are going to look at statistical decision theory. Okay, so which will explain why these algorithms are behaving in the ways they are behaving. Okay, and it will also give us some general template for designing new algorithms. Okay, now we are going to discuss decision theory first for regression, and then we will do the same thing for classification again. So let's start with regression. Okay, so now in the case of regression, I have some input x, okay, which is p-dimensional. Okay, now we are going to consider these inputs and outputs to be random variables. Okay, so now this is a real valued random input vector. Okay, and we have some output y, which is basically a real valued random output variable. Okay, so once I start viewing these things as random variables like input and output, now I can talk about the probability distribution of these inputs and outputs, right? Like, so we are going to call the joint probability as PR of x comma y. Okay, now this is the joint probability distribution of x comma y. Okay, now if you remember, our goal in regression is to find a function f of x. Okay, so for predicting y given values of x, right? Now, to find this function, we always had some loss function. So far, we have seen only one loss function. We are going to see many more loss functions in the future. So we have some loss function which takes both y and f of x as input. Okay, so it takes the true prediction y and the model's prediction f of x, and this is a loss function for penalizing errors in prediction. Okay, now the common loss function that we have seen so far is squared error loss. Okay, which is basically y of f of x, y comma f of x is equal to y minus f of x the whole square. Right? I haven't put the 1/2 here, it's okay. So now, given that the data comes from a distribution, now I can ask questions like, what would be the expected prediction error for a function? Okay, now expected prediction error. Let's just call it as EPE of f. Okay, so I have a function f. Okay, I want to compute the error of this function or the model. Now, I'm asking you to compute the expected prediction error, which means like what would be the prediction error given that the data comes from this distribution, right? Like, so this is expected y minus f of x the whole square, right? Now this expectation is with respect to the data distribution. So I can just expand this expectation. This is basically integral y minus f of x the whole square p of x comma y dx dy. Okay, so I am considering both input and output to be real random variables. So if they are discrete, you will have summation and like things will be similar. Okay, so it's just easier for us if they are discrete. So if they are continuous. Okay, now I can expand p of x comma y. So this becomes integral over x, integral over y, y minus f of x the whole square, p of y given x dy, p of x dx. So what have I done here? Like, so all I did is like I took p of x comma y and treated it as p of x multiplied by p of y given x. Okay, they are both same. Now let's look at this internal integral. Okay. Now, can someone tell me what is this integral? Okay. Yeah.
Is it the same? Is the expected of y minus f of x over 2, knowing x?
Yes. So this is just the definition of expectation in continuous random variables. Okay. So now this is, I'll just put the remaining thing. So this is basically the expected value of this term given my probability distribution is y given x. Okay. So expected value of y minus f of x the whole square given x is equal to some x, p of x dx. Okay. Now, what is the outer integral? That is also an expectation, right? Like it is an expectation with respect to x. So I can write this as expected x, the expectation with respect to x, y given x, y minus f the whole square given x is equal to x. Okay, so now we want to minimize this error, right? So that is our goal. Like, so given any data set, we want to minimize the expected prediction error. So now you can see that given some input x, we don't need to care about other part of the data set. Like we just need to minimize the loss for that input, right? Or in other words, you don't need to worry about this complete term if you want to minimize it. You can take the individual terms and minimize them. That is sufficient, right? Like so it is sufficient to minimize the expected prediction error point-wise. Okay, it means that I don't need to worry about this expectation with respect to x. I can drop it. Okay, so then this becomes, well, I don't know if I had enough space in the bottom. Okay, I did not. Okay, so then this becomes the function f star is going to be arg min of f, e of y given x, y minus f the whole square given x is equal to x. Okay, now, so this is what the goal of regression with least squares is. Okay, so now you can see that we are talking in very abstract terms. I'm not talking about the model itself. F could be anything. Okay, so it could be the linear model that we have seen, or it could be a non-linear model. Okay, so we don't include that assumptions here. So all we are saying here is, if you want to find the best possible model or function f for this regression task with least squares, then this is what you should minimize. Okay, now how would you minimize this? You can differentiate this, set it to 0, and that would be your function, right? So now I'm going to differentiate this term and set it to 0. So dou by dou f of expected value of y given x, y minus f the whole square given x equal to yes is equal to 0. Okay. Now this. So this term here is a minus b the whole square. So I can expand it. So this becomes dou by dou f of expected value of y given x, y square given x is equal to x, plus f square. So I don't need to put expectation for f square because f is not a function of like y, right? So minus twice expected value of y given x is equal to x, multiplied by f, the whole is equal to 0. Okay. So now I can differentiate these things. Like so, like if you can see that the first term doesn't have any f, so the differential is 0. The second term has f squared, so this becomes 2f minus 2 times expected y given x is equal to x is equal to 0. Okay. Now the best possible function that you could find is simply e of y given x is equal to x. Okay. So what did I do here, right? Like so I'm interested in minimizing least square or L2 loss for regression, right? So now our goal is to find some function f which has minimum expected prediction error. And this final equation tells us that the best possible model that you can achieve is basically some sort of conditional mean, right? Or in other words, this says that given some input x, whatever is the mean of y is the best possible prediction that you can do. Okay, so to put it in plain words, right? Like so now if I put it in plain words, this is very intuitive, right? Like so, like let's say for a given x, I show you different values of y. If you want to predict the best possible y, the simple solution is just to tell me the average prediction, right? Like because the average prediction should lie close to most of these predictions. Okay, so now this equation, right? Like so this is known as a regression function. Okay, so I'm going to write explicitly like what I said. Okay, so the best prediction of y at any point x is equal to x is the conditional mean. Okay, when the word best is measured by the least square error or the averaged squared error. Is that clear? Now, this simple calculation tells us what is the ideal function that one can learn from, okay? But this is not the function that we learned with with linear regression, right? Like so now one thing I missed mentioning in the previous lecture is you can also use nearest neighbor for regression. Okay, so nearest neighbor for regression. So can someone tell me how you would convert nearest neighbor algorithm for the problem of regression? Any suggestions? Yeah?
You average the n values of the points around it.
So you basically average n data points around the point and show the average value, right? So if you remember in terms of classification, you took majority voting, right? So instead of that, you can just average. So f hat of x is going to be average of yi given xi belongs to the neighborhood, right? So this is another possible regression algorithm. Like you can do nearest neighbor and regression with it, okay? So first let's try to analyze this algorithm, okay? So now how is this algorithm when compared to the optimal function? So I'll just put it here. The regression function, the optimal function is basically S star. This is the best possible model that you could find, which is expected value of y given x, y given x is equal to x. Okay. Now, this nearest neighbor for regression is making two approximations to the optimal function. Okay. So the first approximation is, instead of using the word expectation, okay, instead of expectation, it's replaced or approximated with average. Right? So you can see that the regression function tells the best possible answer is expected value of y given x. Now, instead of expected value of y given x, nearest neighbor is taking average, which is kind of like a sample expectation. It's expectation based on sample, right? Now, the second difference that you see here is conditioning is relaxed to neighbors. Okay, you can see that instead of conditioning on that particular example x, we are conditioning on the neighbors. This is a practical approximation because you have never seen this example before, right? So if you have never seen x before, you have no data about x. So the best way to approximate that is by just looking at the neighbors. Okay, is that clear? Now, this is a powerful algorithm. Okay, this is a really powerful algorithm because as the training sample size n, right? Like so, as the number of data points grow, okay, the points in the neighborhoods are going to be very close to x. If you have a really large data set, then this approximation, right, this is going to get better and better and better. Okay. Also, as this value of k increases, this average is going to get better and better. Is that clear? So as n increases, okay, the second condition is going to get better and better. Similarly, as k increases, the first condition is going to get better and better. Okay, so now one can show that under some mild regularity conditions on probability of x comma y, okay, as n and k tends to infinity, such that k over n is 0, which means n reaches infinity faster, then the f of x computed by this nearest neighbor regression will tend to the expected value of y given x is equal to x. Okay. Now, this means that for any regression problem that you would face, you could solve it by using nearest neighbor method. Okay, and it is going to get better and better as both n and k increases. Okay, so it looks like we have a universal function approximator, right? It's universal because you can approximate any regression function. Like you bring any data, like you bring any regression problem, you can do it with the nearest neighbor classification. Okay, now does that mean we have one master algorithm for doing regression, right? Like so, like which means we don't need to study any other algorithms and we could stop discussing regression here, right? Like so, the obvious answer is no. So this is not, even though this looks like a really powerful algorithm, there are some issues with nearest neighbors. Okay, so what are the issues? Now, as the number of features increases, okay, this is not as good algorithm as we think it is. Okay, so as the number of features increases, okay, or in other words, in high dimensions, okay, we need very large number of samples. Okay, so this is the problem in high dimensions, okay? And unfortunately, a lot of machine learning applications are high dimensional applications, which will have thousands of features, millions of features, and so on, right? Like so, which means you cannot apply this solution, which looks like an ideal solution in those situations, okay? So now this is not the problem of just nearest neighbor. This is the problem of any method which has this local assumptions, okay? So let's quickly talk about local methods in high dimensions. Okay, now to do that, we are going to consider data to be in cubes. Okay, so we have P features, then we are going to consider inputs uniformly distributed in a p-dimensional hypercube. Okay, so here is how such a cube would look like. Okay, so you can see that this is 3-dimension. In 3-dimension, it's a cube. Okay, it's a unit cube which has entire data. Now, the neighborhood is also defined by smaller cubes. Okay, so in this case, this blue is the neighborhood. Is that clear? Okay, so now depending on how you pick the k value, okay, so you're going to cover bigger and bigger cubes. Okay, now in this case, let us just consider a hypercubical neighborhood. Okay, around any target point, okay, to capture a fraction R of observations. So if I have to capture R fraction of my data set, this is the hypercube. Okay, now you can compute the expected edge length. Okay, let's just call this as EP of R, which is basically R power 1 over P. Okay, if you have to consider R fraction of data, okay, in P dimensions, then you have to cover this much in the cube. Okay, now let us try what would be this length. Okay, if I want to cover just 1% of the data in 10 dimensions. Okay, you can do the calculation, it's going to be 0.63. It means to just capture 1% of the data, okay, I have to cover 63% of the range of my variables. Okay, now this gets even worse. Okay, so if I have to cover 10% in 10 dimension, I have to cover 80% of the range. Okay, now these are not local methods anymore. Like so, even to get, as the number of dimensions increases, everyone is equally far apart. Okay, so like so, if I have to talk about neighbors in high dimensions, my neighbors would probably be the entire data set. So if I have to cover R fraction, like so 10% or 1%, like I would have to cover this entire hypercube. And this is just for 10 dimensions. Okay, this gets worse and worse. Okay, so here you can see that how this thing changes as the number of dimensions increases. Like so, now this is 1-dimensional data. It looks neat, right? Like so, now you can see that from 1 dimension to 10 dimension, like the thing quickly increases. Like so, now even to capture 20% of the data, you have to cover like 84% of the range of the variables, right? So now this basically means that you need lots and lots of data when you're in high dimensions, okay, for nearest neighbors to work. So when I say lots and lots of data, like it's exponential amount of data, and often you will not get that much data, which means practically it's not possible to do this really nice solution, right? Like so this concept that in high dimensions things don't work that well is known as the curse of dimensionality. Okay, so which was introduced and studied by Bellman. Okay, so it's the same Bellman that we saw in the oral course as well, like in terms of dynamic programming, right? Like, so, like, I think the person of dimensionality was also first discussed in terms of dynamic programming, but it's very much more general in other areas of machine learning as well, okay? So there's one thing that I want to highlight here, okay? So what I want to highlight is as the number of dimensions increases, things are going to get complicated, okay? So our intuitions often break in high dimensions. So, which means you have to be careful when I show you visualizations, okay? So when I show you figures, I'm going to show you only 2D, 3D figures because that is all I can see, you can see, right? Like, so we cannot visualize 100-dimensional surfaces and what is going on in 100-dimensional surfaces, which means you have to do a lot of practical experiments to get a feel of it, okay? So all the intuitions, geometric intuitions that you're developing might not extend to high dimensions, okay? So that's the, that's a bit of a warning here. So like, to understand the difficulty of high dimensions, right? Like, so, or when things become too large, like, so, like the prof who taught me AI, like the classical AI course, like, so gave me this analogy. So, like, close your eyes and think about how far is 10 from 15. Imagine there is a line which has all the numbers, okay? So just think about how far 10 is from 15, okay? So now, again, close your eyes and think about how far is 10 power 20 from 10 power 21, okay? Whatever distance you imagine, it is going to be orders of magnitude lesser than what it is really is, okay? So in high dimensions or in like really large, when the numbers are really large, like things behave in a totally unintuitive way. So, so you have to be careful. Plus, this curse of dimensionality tells us that simple methods like nearest neighbors will not work, okay? So, which means the next obvious question is like, what would work in high dimensions, right? Like, so that's the kind of models we are going to see in this course. But before that, like, I want to quickly talk about what is linear regression doing. Okay, so if you remember, linear regression is a totally different type of solution for this problem. So the solution f of x was w transpose x, right? I see the note says x transpose w, so whatever it is, okay? So the function is approximated by using w transpose x, right? So now this is a bit different from how k nearest neighbor is behaving. So in k nearest neighbor, you did not have the concept of model. You just store all the examples and you use them to make prediction, right? Like on the other hand, linear regression is a kind of model-based approach. Okay, so in this case, we are not conditioning on x, right? So instead of conditioning on x, we have used the knowledge of this functional relationship by looking at various values of x and y's to come up with a function w, which is basically the expected value of x transpose x inverse expected value of xy. Okay, now instead of having expectations, we are averaging things from the training data, and this idea of using a model to fit the data, right? So this is going to help us in avoiding this curse of dimensionality, because in this case, I have a well-defined model which has limited number of parameters. Now I'm learning these parameters, right? Like, so, like probably this has only 10 parameters like that you want to learn instead of nearest neighbors, which is going to require lots and lots of examples. Okay, so in one end, you have a totally model-free algorithm like nearest neighbors, which can model whatever, which can fit any arbitrary function that you want. Okay, so in the one end, you have nearest neighbors. It can fit any f, okay? And in the other end, you have linear regression or linear model, let's just say. So this linear model can fit only limited class of f. So this can only fit linear models, okay? However, it doesn't have the high dimensionality issues. Okay, so now when I say it can only fit linear models, then it is kind of immediately obvious that this is not a universal function approximator, right? Like, so I cannot solve every problem by using linear models, while I know that I can solve every problem by using nearest neighbor, given I have exponential amount of data, right? So now, what are the implications of this? So I don't think we can cover the implications in this week, given how slow I'm going. If not, we will cover it in the next week. Okay, so we will talk more about like how these different class of solutions behave this week and next week. So we will stop here and take a 10-minute break. So probably we will continue at 2:47.